Good morning, sir.
Yes. Yeah, is the screen visible?
Yes, sir.
Yes.
Yeah. Let us pass on to the next module. Module number 3. It starts with the first topic is self-organizing map, or otherwise they call it as KSOM. It is coherent self-organizing map. So the coherent is the person, or coherent is the professor who invented or who introduced this concept in the domain of neural networks. So till now, in module number 1, right from your perceptron, your Hep's learning rule, or Hep's network, or your what you can call it as Adaline, what we saw, Madaline, then the next one is nothing but backpropagation network. So all those things, and the next one is this associative memories like auto association, hetero association, then your half-field network, all these things, whatever we saw in the module number 1 and module number 2. So we call all those networks, or we call all these architectures are following the supervised training algorithm pattern, or following the supervised training algorithm pattern. So we have three types of learning, or three types of training. So one we call it as supervised, next one is considered as unsupervised, and next one is nothing but the reinforcement kind of an learning. But of the first two modules we saw is supervised learning techniques. And in the case of supervised learning techniques, so what is done over there is nothing but yeah, external entity or external source will be available, or will be monitoring all our process, how we accept the input, so how we process the input, and how we throw the output to the user or to the required person. So for that we require an external entity. Somebody will be monitoring with us. So that is kind of an learning strategy that is considered as supervised learning strategy. And the next one from module 3, this module we are going to see or we are going to cover is nothing but unsupervised training. So unsupervised training in the sense, okay, the network tries to learn to form their own classifications of training data without any external help. So here there is no external entity or external source or external person will be available, but directly the network tries to train itself. The network tries to train itself, and it tries to produce the output as expected by the user. So mostly unsupervised training may be used for classification problems or clustering applications. Classification applications or clustering applications. But in the case of supervised training, it is for recognition purpose. So verification and other things, validation purpose. But here it is classification and clustering kind of an applications, unsupervised. So that's why they call it as the unsupervised training. The network learns to form their own classifications of the training data without any external help, without the external help. So here how the network learns. So how the network learns and how it tries to classify the training data without any external entity or without any external source. So that is the beauty of the unsupervised architectures, or the unsupervised networks, whatever may be the case. So in order to do those activities, so we have to assume that the class membership is broadly defined by the input patterns sharing common features, and that network will be able to identify those features across the range of input patterns. So for example, you say a set of class consists of a set of students. So in the case of set of students, some students may have certain features. For example, 60 in this class. All 60 may have certain features and different features or independent features. But if you take all the 60 feature set of all the students, okay, we may arrive at some commonality of the features among the student category, that is 60 in the class. So if you try to get some commonality features between the student community, so based on that, so those commonality can be grouped under one category, and the next commonality can be grouped under different category. That is nothing but it may be class number 1 or class number 2 or class number 3 or cluster 1, cluster 2, cluster 3 or group 1, group 2 and group 3. So like that we are trying to execute this task, the unsupervised training. So we assume that the class membership is broadly defined by the input patterns. Input patterns is nothing but so whatever we are going to supply. So that is nothing but the set of inputs sharing the common features, and that network will be able to identify those features across the range of input patterns. So one particularly interesting class of unsupervised is nothing but competitive learning. It works on the principle of competitive learning. Though unsupervised learning or training does not require any external help or does not require any external source. Okay, it uses the concept of competitive learning. So what do you mean by competitive learning? Competitive learning is nothing but, for example, the same soft computing class we will take, 60 in this class are available. So out of 60, only one may become a class topper. For example, he may be scoring 9.2 or 9.3, whatever may be the CGPA. So only one person or one student may be available as a class topper. So, but this competitive learning is nothing but among the 60, okay, all will compete. Among the 60, all will compete, but to the maximum 4 or 5 people may have a closer tough between those students. Closer tough in the sense they may be 9.1 or 9.2, 9.2, 1.5, like that. Some closer resemblance will be there, or closer targets will be there for them. So among the 60, those closer targets will be selected or will be identified by the faculty, and the faculty will motivate all the 5 people. But of course, faculty will motivate all the 60, but the people who are eligible to compete among others and they want to become a topper means, so only those 4 or 5 people may be contributing more in a class of 60, and only one person may come out as a class topper. So the same concept is used over here. So in which the output neurons compete among themselves to be activated, with the result that only one is activated at any one time. So that activated neuron or the competent neuron may be considered as winning neuron or the class topper. Winning neuron or class topper, or winner takes all the neuron. So that is considered as a competitive learning process. So 60 in a class, all 60 cannot go for 9.5 or 10 out of 10. So only one person can go. So that may be considered as a winning neuron. So such competition can be induced or implemented by having lateral inhibition connections. Lateral inhibition connections is nothing but negative feedback paths among the nodes available in the self-organizing map architecture or network. So we are trying to induce such competitions by having a lateral inhibition connections, that is nothing but, which is nothing but a negative feedback paths between the neurons in the SOM architecture or in the SOM network. So the final resultant is that the neurons are forced to organize themselves. Organize themselves in the sense is nothing but so the top 5 students at one, then the next top 10 students will be there, the next top 20 students will be there, next top 30 will be there. So like that, right from the class topper to the last mark. So they organize themselves and then they try to throw the output to the user based on the range of input patterns. So this kind of an architecture or this kind of an behavior which has been given by the set of neurons is considered to be of an unsupervised training. So next one we want to know is nothing but the topographic maps. Before we enter into the self-organizing map, we need to know about topographic maps. So what do you mean by topographic maps? So all our artificial neural networks, this ANN, either it may be unsupervised learning strategies, or it may be an unsupervised learning strategies. Okay, all are trying to mimic the human behavior, or it is trying to mimic the human brain's behavior, whatever may be the case. So the neurobiological studies indicate that there are different sensory inputs, and as we discussed yesterday, so we have different sensory inputs. So what are all the various sensory inputs? One may be visual. Visual in the sense through eyes, I can able to gather or I can able to acquire some information. Then through ears, I can able to acquire some information. That may be considered as auditory channels. And the next one is nothing but the motors. Motors is nothing but the movement of hand, the movement of body position, the gesture positions, the movement of legs, arms, all those things are considered as motor positions. So like that, we have various sensory inputs or sensory organs are there. So what they say, the neurobiological study indicates that there are different sensory inputs are mapped onto the corresponding areas of cerebral cortex in an orderly fashion. Cerebral cortex is nothing but available in the human brain. So whenever I enter into a particular environment, in that environment, I try to visualize certain things. I try to hear something through auditory channel, and I try to feel something through my touch and feel, or through my nose, and I try to perform certain actions through the limbs or the hands or the wrist or my gestures or body positions. All these activities, whatever I am trying to do, these activities are considered as sensory inputs via different sensory channels, and they will be mapped to the human brain. They will be mapped to the human brain, where it will be mapped in the cerebral cortex of the human brain in an orderly fashion. So first what happened, next time t equal to 1, what has been registered, 2 second time second what was been registered, then third time instant what has been registered, like that in an orderly fashion it will be registering. And this form of an orderly fashion of arranging the information in the cerebral cortex of the brain is considered to be a topographic map. That is considered as a topographic map. And this topographic map has two important properties. So what are all those properties are nothing but, so at each stage of representation, so through different sensory channels, it tries to acquire or collect certain informations. At each stage of representation or processing, each piece of incoming information is kept in its proper context or neighborhood. Each stage of representation, maybe at the initial stage, at the middle stage, at the final stage, each stage of representation or processing, each piece of incoming information is kept in its proper context and neighborhood. Proper context and neighborhood is nothing but, for example, scene number 1 I am observing. So I am transferring it to the cerebral cortex of the human brain, and scene number 2 I am getting a different thing. So whether it is related or not, for the scene number 1, scene number 2 is related or not, that may be considered as a neighborhood. If it is related, then adjacent to that it will be kept, or otherwise it will be kept in the different locations. And the next property is nothing but the neurons dealing with closely related piece of information. Neurons dealing with a closely related piece of information. That is nothing but from scene number 1 to scene number 2, I am trying to move. Or I am trying to move my concentration from one position to the other position. There may be some disconnect in the information of scene number 1 and information of scene number 2, or there may be some connectivity between scene number 1 and scene number 2. In such cases, so what I try to do is a thing, but I try to keep the informations of scene 1 and scene 2 closer together rather than keeping them apart. So neurons dealing with closely related pieces of information are kept close together so that they can interact via some short synaptic connections. That is nothing but the connections in the human brain. So what is our interest here is nothing but building a similar kind of a topographic map I need to create. So that topographic map is considered as artificial topographic map, so that learn through self-organization in neurobiologically inspired manner. So how all our inputs from different sensory channels are observed by the human brain, and it is stored in the cerebral cortex in an orderly fashion. They arrange themselves in an orderly fashion. Similarly, okay, I need to create or I need to build an artificial topographic map, okay, which is the base for the self-organizing map, coherent self-organizing map. And how this our artificial topographic map can be built is nothing but it is through an unsupervised learning, that is nothing but in the form of an competitive learning, that is self-organization in neurobiologically inspired manner. So I need to self-organize. I need to rearrange myself according to the situations. So based on that, I try to build this artificial topographic maps. So we shall follow the principle of topographic map formation. So here how the topographic map formation will be done is nothing but the spatial location of an output neuron in a topographic map corresponds to a particular domain or feature drawn from the input space. That is nothing but, so I see something, I observe something from the space or spatial location from a given environment. So that may be considered as an higher dimensional space. That may be considered as a higher dimensional space. From the higher dimensional space, I am trying to map or I'm trying to equate it to a lower dimensional space in the cerebral cortex of a human brain. So next one is how to set up a SOM. So the principal goal of SOM is nothing but I am trying to transform an incoming signal pattern of an arbitrary dimension into one or two dimensional discrete map. So what I said, so in the scene or in the given environment, that may be considered as a higher dimensional space. Why? Because so in a given environment, I may have multiple actions, I may have multiple activities. So I can visualize, I can hear, I can feel, I can act. All these things will be there. So it will be in terms of continuous form rather than in the discrete form. So it is considered as an higher dimensional space, and I try to transform or I try to map that higher dimensional information, continuous information through various input channels or through various sensory channels into a lower dimensional space. So that may be considered as either one dimension or two dimension. So higher dimension to lower dimension, I need to transform or I need to map those activities. So that is considered as a arbitrary dimension into an one or two dimensional discrete map. And to perform this transformation adaptively in a topologically ordered fashion, how the human brain does. So therefore, we need to set up our SOM by placing a neurons at the nodes either in an one-dimensional lattice or two-dimensional lattice. So we need to first decide. So whether we are going to represent it in a one-dimensional space or we are going to represent in a two-dimensional space. So if it is an one-dimensional space, then I need to place the neurons in a one-dimensional lattice. If it is a two-dimensional space, I need to place it in a two-dimensional lattice. So higher dimensional maps are also possible, but for the practical application point of view, we are restricting maximum to one or two dimension, not the 3-dimension and 4-dimension. We are not utilizing. Then the next one is nothing but the neurons become selectively tuned to various input patterns or the classes of input patterns during the course of competitive learning. Selectively tuned in the sense is nothing but based on the commonality of the features or based on the common features, it automatically tuned themselves to various inputs, whatever I am trying to supply, and it tries to segregate themselves into various classes of informations. That may be class A, class B, or class C, or cluster 1, cluster 2, or cluster 3A. So the location of neurons so tuned, that is nothing but the winning neuron become ordered, and the meaningful coordinate system for an infinite features is created on the lattice over here. So this is nothing but the mapping or the transformation. So this may be considered as an entire scene. This yellow color image can be considered as an environment. So this is a continuous high dimensional input space because continuously I may able to grab or I may able to attract or I may able to collect certain informations via various sensory input channels. So from here, whenever I try to map or whenever I try to transform the information from this dimension to this discrete low dimension, this discrete here, since this information is continuous. So the continuous information is segregated via a frame by frame concept or scene by scene concept. So from this X, so it is transformed to a discrete low dimensional output space. Either it may be of an one dimension lattice or it may be of a two dimensional lattice. So X is transformed or X is mapped to a I of X. So I of X is nothing but this lower dimensional space representation. And this I of x, again, from here, lower dimensional space to continuous high dimensional space, also it is possible. That is considered as Wi of x. So each point I in the output space will map a corresponding point W of I in the input space. W of I in the input space, and pi is nothing but your feature map. So how we are trying to create that one-dimensional lattice or two-dimensional lattice. So coherent network, we shall, this is a normal one. So how the human brain maps. Similarly, we are trying to create a coherent network. We shall concentrate on particular kind of SOM is called as coherent network. So it has a feed-forward structure with single computational layer arranged in rows and columns. So this may be considered as rows, and this may be considered as columns. So it is arranged in rows and a column, single computational layer. Only one layer will be there. So here it is input layer. So from input directly it goes to the computational, and from the computational I can able to get the output over there. So each neuron is fully connected to all the source nodes in the input layer. Each and every neuron will be connected over here as seen in the diagram. So this is a one-dimensional map with will just have a single row or a single column in the computational layer. If it is a two-dimensional means, so you may have a different representation. So what are all the components of SOM? What are all the components of SOM? So in the self-organizing process, there are four major components are there. There are four major components. So one is nothing but as we discuss in the supervised learning architecture or in the supervised learning networks. So the first step here also it is initialization. But in the case of unsupervised, it uses the concepts of competitive learning. So second step goes, or second component involves is nothing but the competition. And third one is nothing but cooperation after the competition, and the final one is nothing but adoption is nothing but so whether they belongs to the same category of same feature set or different feature set, that is nothing but the adoption. So it involves four components. The first one is nothing but initialization, second one is nothing but competition, third one is nothing but cooperation, and the fourth one is nothing but the adaptation. Okay, adaptation. So what is initialization? As we do in supervised learning networks, here also we try to initialize the connection weights with the small random values. Initialize the connection weights with the small random values. Then in the competition, for each input pattern, the neurons compute their respective values of a discriminant function which provides the basis for the components. There's nothing but each input pattern. So I try to supply, I try to supply something from the high dimensional, continuous high dimensional space. I try to map that to a discrete low dimensional space. That is, it may be a one dimensional lattice or it may be a two dimensional lattice. For that, for each input pattern, the neurons compute their respective values of discriminant function, which provides the basis for competition. So the discriminant function here is nothing but what you can call it as equivalent distance measure they may use over here. So for each input pattern, the neurons compute their respective values of the discriminant function, which provides the basis for competition. The next one is nothing but the particular neuron with the smallest value of the discriminant function is declared as the winning neuron. That is nothing but a winning neuron. So here each and every neuron may have some values. Each and every neuron may have some values, and with the help of that values, it tries to calculate it tries to calculate or compute those values via the discriminant function, which may be considered as the basis for competitions over here. And then the neuron with the smallest value will be declared as the winner of the competition. Then the next process is nothing but cooperation. The winning neuron determines the spatial location of topological neighborhood of excited neurons, thereby providing the basis for cooperation among neighboring neurons. So what they have given, winning neuron determines the spatial location of the topological neighborhood of excited neurons. So for example, I said, so we have only one person to be the class topper, but 4 or 5 persons may be closer to that topper. So that is nothing but cooperation. So winning neuron determines the spatial location of topological neighborhood of excited neurons. So they are also taking part in the firing process, but they failed due to that one particular neuron has a higher value of excitement, or they have an higher firing strength. So due to that, that one neuron may be considered as the winner neuron, and other neurons may be considered as the neighborhood excited neurons. So they provide the basis for cooperation among the neighboring neurons. Next one is nothing but adaptation. So the excited neurons decreases their individual values of the discriminant function in relation to the input pattern through suitable adjustment of associated weight connection weights, such that the response of the winning neuron to the subsequent application of similar input pattern is enhanced. So adoption is nothing but the excited neurons. So it computes some value, and it took place in the firing process. It took place in the firing process, and it tries to take part in the competitive learning process. So in that case, it computes certain values, and that values will be decreased via the discriminant function relation to the input patterns. And based on that, we consider that that is also adopted in the firing process, that is also suitable, considerably suitable for taking part in the firing sequence or in the firing actions. So the first one is nothing but initialization. Second one is nothing but that is randomly with some small values. Second one is nothing but the competitive process. So if the input space is d-dimensional, if the input space is d-dimensional, we can write the input patterns, that is nothing but from high dimensional vector. Okay, so we can write the input patterns as x. So x is nothing but this one. We can write this as x. It is a high dimensional input space. So that's why they call it as input space is d-dimensional. If there are d inputs, we can write the input patterns as x equal to xi equal to I equal to 1 to d, and the connection weights between the input units I and the neurons j in the computation layer can be written as wj equal to wji, which is nothing but j takes the value 1 to n and I takes the value 1 to d, where n is nothing but the total number of neurons in this topological map. So then we need to define our discriminant function. So that is nothing but Euclidean distance formula. Discriminant function is nothing but Euclidean distance formula. It is squared Euclidean distance formula. So dj of x equal to summation of xi minus wji square. In other words, neuron whose weight vector comes closest to the input vector is declared as the winning neuron. Okay, so in this way, the discriminant function is calculated. There is nothing but square of Euclidean distance between the input vector and the weight vector wj for each neuron j is computed, and the value closer to the input vector is considered as the winning neuron. Next one is nothing but cooperative process. In the case of cooperative process, so we find that there is a lateral interaction within the set of excited neurons. Lateral interaction in the sense is nothing but negative feedback. When one neuron fires, its closest neighbor tend to get excited more than those further away. So for example, if I say that this fellow is always getting rank number 1, so by that I am motivated that I need also to take part in the competitive process, then I need also to score rank number 1, but I failed. Instead of getting rank number 1, I may be rank 2 or I may be rank number 3. So that is nothing but the value, or that is nothing but the tendency of the neighborhood neurons. That's why they call that when one neuron fires, its closest neighbor tend to get excited more than those further away. That is nothing but if you see here, you consider that I am trying to fire this particular neuron. I am trying to concentrate. It tries to take part in the firing process. So along with this neuron, this neighborhood, either it may towards the left or towards the right, or top or bottom or in the diagonal positions, these 8 neurons may take place. These 8 neurons may take place in the firing process, but they may fail because they may not have such firing strength. But the other neurons, in this one-dimensional lattice or two-dimensional lattice may not be taking part in the firing process because the distance from here to here, the other neurons may be somewhat larger. So in order to excite those neurons, it is impossible. So the distance also plays a major role. That's why they say that it decays with the distance. So as you may have a longer distance or you may have more distance. So those neurons will not be taking part in the firing process. Only the neighboring neuron will be excited and it will also be taking part in the firing process. That is considered as cooperative process. So we want to define a similar topological neighborhood for the neurons in our SOM. So if Si of j is lateral distance between neuron I and neuron j. So from this, sorry. So maybe consider as from this may be from one neuron to other neuron. Okay, that is nothing but Sij. It may be lateral distance from one neuron to the other neuron, neuron I and neuron j on the grid of neurons. We take the topological neighborhood Tj, I of x. Tj, I of x is nothing but, so this is nothing but I of x. T is nothing but the topological, T is nothing but topological neighborhood. So from I to j, that is nothing but Tj of I of x, okay, which is given by this equation, which is exponential of minus s squared j I of x divided by 2 sigma squared, where I of x is nothing but the index of the winning neuron. You can see here I of x is nothing but the index of the winning neuron. And this has several important properties. It is maximal at the winning neuron and it is symmetrical about that neuron. It decreases monotonically to 0 as distance goes infinity. For example, so if it moves from this position to this, so it value becomes 0. If it is closer to the things, then it may take part in the firing process, and next time it may be considered for firing also, and it may be considered as winner neuron. So that's why they call it as. So it is a maximal at the winning neuron and it is symmetrical about that neuron and it decreases monotonically to 0 as the distance goes infinity. That was they have given. A special feature of SOM is that the size of sigma is something but the size of the neighborhood needs to decrease with the time. So for example, it may be maybe considering only the what you can call it as what you can call it as 4 neighborhood, or you may consider 8 neighborhood, or you may consider 16 neighborhood, like that. So the neighborhood size sigma has to be concentrated during the competitive process. So the popular time dependence of an exponential decay is given by this formula, sigma of t equal to sigma naught into exponential of minus t divided by eta over here. And the next one is nothing but the adaptive process. So adaptive process is nothing but our SOM must involve some kind of adaptive or learning process by which our outputs become self-organized and feature maps between the inputs and the outputs are formed. So here must involve some kind of an adaptive or learning process. Output becomes self-organized and the feature map between the inputs and the outputs are formed. That is something but I try to supply certain input patterns, and based on the input patterns, the SOM accepts the input patterns and it tries to reorganize among themselves via these 3 components. One is initialization, next one is nothing but the competition, and the next one is nothing but the cooperation. Via these 3 components, it tries to reorganize via these components based on the common features, and it tries to throw the outputs for the inputs supplied over there. So the point of topographic neighborhood is not only the winning neuron, it gets its weights gets updated, but also the 8 neighborhood or 4 neighborhood or 16 neighborhood, whatever, or 32 neighborhood, whatever may be the case, the neighborhood neurons weight also will be updated. So that is the adaptive process. So the weight updated of the winning neuron alone is not updated. Even the neighborhood, for example, the top, bottom, left, right, the diagonal positions that may be considered as 8 neighborhood positions. For that 8 neighborhood, the neighbors' weights are also updated. So the next time that may be taking part in the winning competition or in the competitive procedure, and that they may be considered as winner for the subsequent iterations or for the subsequent cycle of times. So in practice, the appropriate weight updation equation is given by the formula delta Wji equal to eta of t into Tj of I of t into x minus Wji. Okay, so this t is nothing but time epoch, and this eta of t is nothing but your learning rate. Eta is nothing but learning rate, and it is expressed by this formula. And the effect of each learning weight update is to move the weight vectors Wij of the winning neuron and its neighbor towards the input vector. So this we will see how it goes. And the next one is nothing but the ordering and convergence. So how long it will reorder? How long it will reorder? Okay. So whether for the first iteration, second iteration, third iteration, fourth iteration, or first epoch, second epoch, third epoch, how many times it is trying to reorder themselves? Okay, that is very important. So ordering or self-organizing phase. So provided the parameters eta naught and other these four parameters are selected properly, we can start from the initial state of the complete disorder, and the SOM algorithm will gradually lead to organize the representation of the activation patterns drawn from the input space. So initially it may be at one set of order, but as we try to supply the input patterns, and as the unsupervised and the competitive learning starts, it try to gradually reorder themselves in a step-by-step fashion, and it tries to provide an final output to the user from the high dimensional input space to the lower dimensional output space. So that's why they call it as. So it will gradually lead to an organized representation of activation patterns drawn from the input space. There are two identifiable phases of this adaptive process. One is nothing but ordering or self-organizing phase. Next one is nothing but convergence. So when I try to complete my iteration, or when I try to stop my training process, or when I need to stop my process. Okay, that is nothing but my convergence phase. So ordering or self-organizing phase is nothing but during this phase, so which the topological ordering of the weights vectors will be taking place. So this will take as many as 1,000 iterations of the SOM algorithm, and the careful consideration needs to be given to choose the neighborhood and the learning rate parameters. So these parameters, these four parameters needs to be properly selected, and to the maximum it may take 1,000 iterations to reorganize themselves. So that is nothing but the first step in the adaptive process during the competitive learning process. The next one is nothing but the convergent phase. So in the case of convergent phase, okay, during which the feature map is fine-tuned and comes to provide an accurate statistical quantification of the input space. So convergence is a thing, but almost so initially in the first iteration, second iteration, third iteration, fourth iteration, fifth iteration, 1,000th iteration, it tries. And finally, I say that in 1,000th iteration, I am going to converge to the maximum, or in 10th iteration, I need to converge. Like that, I try to do it. So for that, how many iterations are required for convergence? So here, number of iterations in this convergence may take at least 500 times the number of neurons in the network, and again the parameters must be chosen carefully. So this convergence as well as this ordering or self-organizing is based on only these four parameters. So we can see the process. So how it self-organizes to each other. So this is nothing but 4 data points. This blue color cross marks are considered as 4 data points in our continuous 2D input space. This may be a continuous 2D input space. So we are not taking a high dimensional input space, but instead of high dimension, we have taken as a 2-dimensional continuous input space, and we want to map these 4 points in a discrete 1-dimensional output space. 1-dimensional output space. So the SOM grid structure is nothing but 1-dimensional lattice over here. So the output nodes map to points in the input space. The output nodes map to the points in the input space. There's nothing but your circles. So random initial weight starts the circles at random positions in the center of the input space. So I randomly pick one of the data points. So for example, I pick this data point, cross in the circle. So I try to pick some data point over here. Okay, the closest output point represents the winning neuron is nothing but this solid diamond. So for this, the closest one is nothing but this solid diamond. So among this outputs, so the closest pattern, it maybe belongs to this particular classification or this particular category. So this may be considered as a winning neuron, and this moves towards this input pattern. The winning neuron is moved towards the data point by a certain amount, and the two other for this, which is the neighbor. So this is considered as neighbor and this is considered as neighbor, closer distance. So that two neighbor is also moved by some small measurement. And next we randomly pick this. So for this may be considered as a closest output point. So this may be moving towards this, and the near neighboring point also will be moving towards this. And again we pick this one. So for this diamond may be considered as a nearest point. So this will move towards, this may be considered as winning neuron. So this move towards this, and this neighboring neuron also will move towards this. So this is nothing but the representation over here. So apart from this, we have the neighbor topologies in coherent. So we have various types of topologies are there. So but here with respect to coherent self-organizing, so we use two types of topologies. So one is considered as rectangular grid topology. In the case of rectangular grid topology, so it has 24 nodes in the distance of two grid, 24 nodes in the distance of two grids, and 16 nodes in the distance of one grid, and 8 nodes in the distance of 0 grid. So see here, so 1, 2, 3, 4, 5, 6, 7, 8. So this may be considered as 0 grid. So I have only 8 nodes, and in 16 nodes in grid number 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 nodes in grid number 2. And 24 nodes in grid number 3. Okay, so these are all nothing but the rectangular grid topology. So whenever I consider that this is a winning neuron, so all these neurons will take part in the competitive process, and it may also take part in the adoption process. The next one is nothing but the hexagonal grid topology. So in the case of hexagonal grid topology, 18 nodes in the distance 2 grid and 12 nodes in the distance grid 1 and 6 nodes in the distance grid 0, which means that difference between the each rectangular grid node is 6. You can see 18, 12 and 6. It is in multiples of 6, and the winning neuron is indicated by the hash symbol. See here, this is winning neuron. So this is grid number 1, I have 6, and this is grid number 2, I have 12, and this is grid number 3, I have 18 neurons. Is it clear? So this is self-organizing map, coherent self-organizing map. So this architecture is similar to that of competitive network. So X1, X2, X3 up to Xn is nothing but the input supplied towards the things. And with the help of the neighborhood schemes, one is either I may go for a rectangular grid or I may go with the hexagonal grid. So I try to process the input pattern, and I try to get the outputs over there. This is the algorithm. Take down step number 1, initialize the weights, learning rate alpha and the neighborhood topological scheme. Step number 2, I need to continue steps 3 to 9 when the stopping condition is not true. And step number 3, I need to continue step 4 to 6 for every input vector x. And step number 4, that is nothing but your discriminant function, which is nothing but Euclidean distance method. So dj equal to xi minus wij whole square. And the next one is step number 5. It is obtain the weight, obtain the winning unit j, where dj is minimum. Then step number 6, I need to calculate the new weight of the winning unit by the following relation: wij new equal to old value into alpha into this. So alpha may be considered as learning rate parameter. So xi is nothing but the input, and wj is nothing but the weight value associated for the winning unit. And this step number 7, I need to update the learning rate alpha by the following relation: alpha of t plus 1 equal to 0.5 into alpha t. T is nothing but the time factor. And step number 8, reduce the radius of topological screen. So either from grid 1 to grid 2 or grid 2 to grid 3. Like that, grid 3 to 2 or 1, I need to reduce the radius. And step number 9, I need to check for the stopping condition for the convergence of the network. So if the stopping condition is true, then I am going to terminate. If not, I am going to continue the process. So with this, we will wind up today. So next class, we will go with the problem. So is it clear?
Yes, sir.
Thank you very much.